Assalamu alaikum warahmatullahi wabarakatuh. I'll explain this part over here. This slide is made for subject computational intelligence and made by Dr. Schaffner, and it's explaining the genetic algorithm and what's genetic algorithm in general. So genetic algorithm is taken from the chromosome over here, and you have genes, chromosome, and population. So what's genetic? From which branch we get the genetic algorithm? So genetic algorithm is coming from the evolutionary algorithm, and the evolutionary algorithm coming from the guided random search technique, and from guided search techniques coming from classes of search techniques. And there is some explanation over here. Genetic algorithm is developed by John Halland 1975, so it's been like 25 40 45 years since genetic algorithm is being outside, inspired by the biological evolution. So it's actually the biological principle uses concept of natural selection genetic algorithm. In Darwin, we don't agree with this person, but that's it. Particularly well suited for hard problems where little is known about the underlying search space, widely used in business, science, and engineering. So we actually use it. We don't care about this. We actually use it in science, engineering, and everything. It's like everything else. Uh, Genetic algorithm maintain a population of candidate solution for the problem in hand. It makes it evolve, iteratively applying a set of stock operations and the selection reptile. So as you can see over here, this slide is a very good slide. We have like pictures. We can understand the slide by pictures. And this guy, this is the father number one, and mother number one over here, and this is their son, and this is the first generation, the second generation. So the son will take the best features that most likely he needs, like in his to survive. So he'll take the eyebrows from the mother, he'll take the hair from the mother, but he will take the nose from the father, and maybe the mouth, and that's it. This The whole thing. This is the selection for the son. And next one, genetic algorithm process. So we have while, termination condition, not met, set filter. So very boring stuff. Recombine, crossover between individuals, mutate individuals. Step by step genetic algorithm for function optimization problem. We have the problem over here. So if x equal to x to the power of 2, where x varies between 1 and 31, we will go through the table. So start doing this. So we have this set of the table, like in the exam we have 0 1 1 1 0 0 and decision variable. So we'll get it like it's 2 to the power, like the binary to decimal over here, and from decimal to the power of 2, we get to the power of 2 over here. So the sum, the mean divided by 4, and the maximum, the highest number is this. We go over here like 144. Now divide this over the sum, we get a value over here, which is 12%, 31, 21, and 2 point, like over here. And expected count, how to get the expected count? So we take this value over here, divided by the mean. Yes, we take this value divided by the mean, we get 0.12, and we take this value divided by the mean, and we get 0.5411, like this. So this expected count. So how to get the roulette wheel? So to get the roulette wheel, so we round this to the closest number. So 1.2 is actually 1, 0.45 is actually close to 1, because it's 1 point. 2.1 is gonna be 2. 0.0 is actually very close to 0, so it's gonna go to be 0 over in this place. And also apply recuperation crossover operation. A single point crossover is performed and new offspring changer is produced. So we have this is the first offspring, like all the numbers, we put all the numbers over here, so they have put all the strings over here. So those two acts together, like this is of two fathers, like the father and the mother, and crossover points. So uh, in here, like we choose three um, over here, and we take two values from here, like these two values, and put it in there, and these two values, and this stay the same, like this they stay the same. The first t here stay the same. When the cross point is 3 3, this stay the same, and this will be in here, and this will change to be in here. That's it. And the next one is gonna be the same, like we cross over 2, so we take the 2 in digits over here, and we put these three values to this, and put these three values to this, and this will stay the same. So the next one, like before the crossover, after the crossover, we get the same variable x, and after the z to the power of 2, the sum, mean, max again. And here mutation chromosome, so we choose this. Actually we can put the one over here, we can put the one over here, but it should be on, it cannot be 0 1 1 in this part, it is random. So we can, this is not like necessary to be zeros or something, but we can put zeros sometimes. We can put one over here, one over here, one over here. We can put full zeros, or one value for the better, like offspring children after. So we just add this one to this part, like over here. So we just have it over here like this, and we get these values, and we get to the power of 2, so it's gonna equal to this, so the sum, so the mean over here and the max value. So stop the cycle generation and evaluate. So we actually get the first generation, second generation, third table, first table, third table, second table, third table, and we calculate the mean, and we realize that the sum is just growing, keep growing like this. And we do a calculation, like one paragraph of explaining the first part, the second part, for example, the third part, or we can explain the first part for the sum, the second part for the something else, these numbers, as you can see over here. And the slide is finished. So this is perfect slide, I like it. So I'm